All right, so let's see what the first worked example wants. This is a vapor pressure lowering example. It says calculate the vapor pressure lowering of water when 5.67 grams of glucose is dissolved in 25.2 grams of water at 25 degrees Celsius. These are standard conditions, right? The vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury, right? This is a unit of pressure. We have torrs and we have millimeters of mercury. We can have them as units of pressure. Don't be scared, right? We could have torrs and we could have these millimeters of mercury. So these are just units of pressure, right? We've talked about it. Now we go for it. What is the vapor pressure of the solution? So this question is asking for two things. The first thing is the vapor pressure lowering, then the vapor pressure of the solution. Now, we have seen that we have a law which we use for vapor pressure lowering, which is just the fact that we have the pressure above a liquid going down if you add more solid. Because the pressure above a liquid is simply telling you, in simple terms, it tells you how much, or it is telling you how easy it is or hard it is for molecules in the liquid to change to gas phase. How easy is it for the molecules to change into gas phase? Now, if we put solute, the molecules in the water are blocked. It is now harder for them to change into gas phase because we now have some solute. We now have some other particles that are on the surface that are blocking the particles of the liquid to change into vapor. So it's harder. So the vapor pressure goes down because less particles can change into vapor, right? So either way, we don't have to know too much. We've talked about it. But now what we want is the calculation to say, right, this vapor pressure lowering, how does it happen? We said Raoult's law, which was an important one, simply said this, and there are many different ways to write it. He says that the pressure of the solution, but we like to say, from your lecture slides, pressure of solvent. This is the final pressure of the solvent, which is the pressure of the solvent after you have put the solid. This is equal to, this X means mole fraction of the solvent, which means total number of moles of the solvent divided by all the moles that are in the solution. So it's now solvent plus solute. So it's number of moles of solvent divided by the number of moles of solvent plus solute together, the whole solution. So it's the mole fraction. So it is moles of solvent over total moles, right? That's a ratio. So we'll say that this is the mole fraction of the solvent. If we want the mole fraction of the solute, we'll say moles of solute divided by total moles. But here we want the moles of solvent. So the final pressure of the solvent, this is our Raoult's law. Remember, that is we call it Raoult's law. I'm writing it again. Raoult's law, right? The final pressure of the solution, okay, this is the solvent in the solution after we've added the solute, is equal to the molar fraction of the solvent times the initial pressure, which is P0 of the solvent, okay, times the initial pressure. So we can say it's just the pressure of the pure liquid. So we'll say, if you want to know the final vapor pressure of water, you multiply the molar fraction, how many moles of water over the total moles for that solution, times what was the vapor pressure of the water before you added the solid. Then we'll be able to find the final vapor pressure. But this is not what we really want. What we really want comes from this idea. We then derive, which I won't do again, But we saw that what we really want comes from the idea that the mole fraction of the solvent plus the mole fraction of the solute. Remember, these will be ratios. This will give you a total of 1. Remember how you get mole fraction. Total number of moles for that is the number of moles for that guy over the total number of moles in the solution. So mole fraction of solute will be saying how many moles of solute do we have divided by what is the total number of moles for the solution. So what we know is that these two add to 1, right? And what it means is that if I take solute to the other side, I'll have molar fraction of solvent being equal to 1 minus the molar fraction of the solute. So I can go where there is the mole fraction of the solvent and change it to be 1 minus the molar fraction of the solute. And we know what that leads us to. We would now end up having the final pressure of our solvent, which is the final pressure of the solution in actual fact, is therefore equal to pressure of the, I shouldn't derive again, the molar fraction of the 1 minus, let's say, the molar fraction of the solute, 1 minus the molar fraction of the solute, times the final pressure, times the initial vapor pressure of the solvent, sorry. And this would lead us to the two important formulas that we use. That would be, remember, that first, I won't derive again. You check the deriving video, but it's not important. The pressure, the formulas which we would need, this is Rhodes' law, but we won't use it like that. The one we need is that the change in vapor pressure, which is just going to be equal to, remember, this is the decrease, right? Vapor pressure lowering. Now, anything that says lowering, if you want to find anything that says lowering, you say initial minus final, because we always want our answers to be positive. So since we are lowering, we know the final is going to be less. So anything that says lowering, it's initial minus. So it will be the initial pressure. We want the vapor pressure. So it's the initial vapor pressure of our liquid. So it's this 0 means in original, initial, this O, right? Minus the final, okay, of our liquid, right? And this is also equal to, from our derivation, we'll see that this vapor pressure lowering is going to be equal to the molar fraction of the solute times the initial pressure of the solvent. This is so good, because what we have just done is we no longer have the final, we now have the change in vapor pressure. So in here, this was Rhodes' law is just for final, but now we have the change. So let me erase it and let's answer our question. You watch again the previous videos. Sorry for repeating myself. Now, I'll go and say the two formulas which we needed were for vapor pressure lowering. So what we've seen is that vapor pressure lowering, delta P, we can start by saying it is equal to the molar fraction of the solute this time, not of the solvent. Of the solvent is just for the final pressure, right? For of the solvent, we saw that we would be looking for the final pressure of the solvent. That is the one that is, we say, final pressure of the solvent. Final pressure of the solvent is equal to the molar fraction of the solvent times the initial pressure of the solvent. But here we are saying vapor pressure lowering is the final of the solid, is the molar fraction of the solid rather, times the initial pressure of the solvent. So all we are changing is this guy. Then this will become delta P, right? All right. Now we've seen again that delta P is just final pressure, okay, is initial pressure, sorry, minus the final, because it is a lowering, right? All right. So we'll use these two. So now let's go ahead and let's find what we want. What is the first thing we want? Calculate the vapor pressure lowering when you have 5.6 grams of glucose and this grams of water. So the first thing which we want is to be able to get X. That's the first thing which you need. Now, to be able to get X, remember, it's all about number of moles. So first, I want to find the N, which is number of moles of glucose. So of C6H12 or 6. This is going to be mass over molar mass. Remember that number of moles is equal to the mass which you are going to be given in grams over the molecular mass which you get from adding all the atomic masses from the periodic table, right? So we'll say, what is the mass? We've been told we have 5.67 grams over, what is the molar mass? We have 6 carbons. You check on the periodic table. The mass, which is the bigger number. Carbon, we have a mass of 12. And how many do we have? 6 of them. So it is 6 of 12s. Plus, hydrogen has a mass of 1. So it'll be 12 by 1. Plus, oxygen has a mass of 16. So it'll be 6 by 16. You can check on the periodic table. These are all grams. Okay? And we can be able to get our number of moles. Then we can also get number of moles of water, right? Okay, and this is obviously steam because it's water at 25 degrees Celsius. Okay, some of it is liquid. So of water, what is this going to be? What is the what are the grams? 25.2. So 25.2 mass over mR over what is the molecular mass? We have 2 hydrogens to be 2 by 1 plus 1 oxygen, which is 16. So we can get it. Now let's put it. This becomes 12 by 6 plus 12 is okay, so this was 180 at the bottom, and 5.67 divided by 180 gives you 0.0315 moles. So here our answer is 0.0315 moles. Then in here it will be just 25.2 over, this is 18. Okay, so if you want, you can put 25.2 grams over 18 grams because this is molar mass, right? Okay, so 25.2 divided by 18, we get exactly 1.4. So this will be 1.4 moles. Now we have it. Great. So let's go ahead and let's start to find. I can say that X solvent, the molar fraction of the solvent, although I'm not going to need it, this is just going to be number of moles of solvent over total number of moles, total N, which is going to be, what's the number of moles of solvent? 1.4 moles over, what is the total? 0.0315 plus 1.4, and these will be moles. So over the total, which is for the solute and the solvent. So for this glucose and the water together, we add, then we'll find our solution. So it is going to be 1.4 plus 0.0315. We'll get 1 point blah, blah, blah. Then we can now say 1.4 divided by that. We'll get 0.977, blah, 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 blah. So we could have this 0.9779, blah, blah, blah. So 978 moles. Now, what we know is we can get again for solute, which is the one which we actually want. And we can get it. What would be the mole fraction of the solute? Maybe let's not even put for the solvent because it's a waste of time. Okay, we're not going to need it. We're not going to use it, bro. So we can just say for our solute, we can say X solute. We could have said it is 1 minus the solvent, but to be more exact, yeah, we can do that maybe. We'll put more decimal places, 0.978, right? Then we would say 0.9779. So yeah, 0.978 moles. We can say that X solute, although I would prefer you calculate it directly. For this, I'm just going to do it. 1 minus X solvent, which is just going to be equal to 1 minus 0.978. That is, so we can say 1 minus solution. You get 0.022. Okay, this is 0.022 0 blah 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 moles. So this would get it as 0.022 0 moles. there we go. If we put it to 3SF, it's 0.0220 because these two zeros are insignificant. We don't count them. They are in front. We only count the one at the back. So now that we have the X, we can now just get our vapor pressure lowering. We now say that delta P, that's our vapor pressure lowering, is just going to be X solute, okay, X solute times the initial pressure of the solvent. Is it true? Exactly. It's very true. So now what are we going to do? We just go to pick it up. Let's go and get it. What would be our initial pressure of the solvent? The vapor pressure of the solvent is this, 23.8 millimeters mercury. So it's going to be our answer 0.0220. It's moles over moles, so it's not moles. Yeah, these are not moles. This fraction is moles over moles, so it has no unit. 0.0220 times what was the value? 23.8 millimeters mercury. So times 23.8 millimeters mercury, and this, what is it going to give me? 0.220 times 23.8, I will get 0.5237 blah blah blah. So I'll round it off to 0.524 millimeters mercury. Okay, our vapor pressure lowering will have the same unit as our pressure. So if the pressure is in millimeters mercury, it'll be millimeters mercury. If the pressure is in torrs, it will be in torrs. Now that is the first one. Now the second one is saying calculate the vapor pressure of the solution. So that's the final one. Now remember that we say delta P is just equal to pressure of the solvent, the final, minus the initial vapor pressure of the solvent. So it's just P0 of the solvent. So now to get the final, I'll have to take the initial to the other side. I'll say delta P plus the initial of the solvent should then give us the final one. So what would it be? It's going to be, what is our delta? Sorry, I've put it wrong. Our vapor pressure lowering is actually the initial of the solvent minus the final, because it's reducing. So it's always initial minus final. I'd almost done wrong here. So we want this guy. So we'll take him to the other side and then take delta P to this other side. So we'll say that the final is equal to the initial minus the change, because we are lowering, minus the change. So therefore, I'll say it is the initial was 23.8 millimeters mercury minus the change 0.524 millimeters mercury. Then I can get the final. So it'll be 23.8 minus 0.524. And I'll get 23.276 millimeters mercury. Okay, that is what you can do. And you round off to three significant figures, it will be 23.3 millimeters mercury. And you are done with this question. You have answered everything. Well done.